Yesterday we did this 9.9 independent of path, and then fundamental theorem, and when it is closed, the answer is 0. And if E is electric field, when we say that E is electric field, then it is conservative if it can be written as negative time gradient of V, and if it is any vector field, then simply gradient of V. When it is electric field, then we will say negative time the gradient of V. So let me include here, if it is electrical field, then what will be the difference? This is negative time gradient of V. And we will have here a negative sign, and this will become positive. So the final answer at the end, it will be negative. And work done by a force in moving a charge from a point A to another point B in an electric field, it follows from Coulomb's law that it is equal to negative Q time E dot dl. And what is about this electric field and this potential, etc.? It is from section 4.7 from the other book. So let us section 4.7. Electric potential. So first of all is work. The work done or the potential energy required in moving a charge Q from A. Actually, this A is a point, Q is charge, and point A to point B is W is equal to negative Q from A to B E dot dl. E dot dl potential difference between 2 points A and B potential difference between the points A and B is V sub AB, and that is equal to W over Q, and it is negative A to B E dot dl. Where A is the initial point, B is the final point. If VAB is a negative, there is a loss of potential energy in moving Q from A to B. This implies that the work is being done by the field. However, if VAB is positive, there is a gain in the potential energy in the movement, and an external agent performs this work. VAB is independent of path taken, and it is measured in joules per coulombs. So I think you electrical engineer, you are very much familiar with this one. With this note, VAB is measured in joules per coulomb, commonly referred to as volts. Okay.
Doctor, E is the energy, right?
E?
Yes.
Here E is the electrical field.
Okay.
E is the electric field. Okay. Here let us do some more questions. Example. Let E be the electric field. Let E is equal to 2 rho sine phi A rho. So it means we are working in cylindrical coordinates plus rho cosine phi A phi plus 3z square AZ be the electric field on a certain region of space. Okay, then what do we need? Verify that E is conservative. Part B. Find the electric potential V. And then part C is use fundamental theorem and potential function to evaluate. Use the fundamental theorem and potential function yani V to evaluate integral 2 pi over 6 negative 3 to pi over 6 negative 3. This is point A, and 4 pi over 2 and 2 to this point B, E dot dl. Evaluate this integral, and then part D is calculate the work done in moving. Calculate the work done in moving in moving a 5 microcoulomb charge from A 1, 0, negative 2 to B 4 pi over 2 1. So this is another, say, set of points. Now the solution starts from here. Part 1 is the to verify is conservative. For this, we will compute curl of E, yani del cross E. We will compute del cross E, yani curl of E. So here is a row unit vector, a phi unit vector, a z unit vector, then partial over partial row, partial over partial phi, partial over partial z. Then what is function 2 row sine phi, row cosine phi, 2 row sine phi rho cosine phi and 3z square. Okay, now let us evaluate this. This is equal to a rho, and then we multiply partial over partial phi of 3z square is 0, minus partial over partial z of rho cosine phi is also 0, minus a sub phi partial rho over partial rho of 3z square is 0, minus is also 0, plus a sub z is also, so it is a 0 vector. Therefore, we say that E is conservative. Okay, when E is conservative, there exists a potential function phi
Doctor, for AZ, it is not 0 minus 0, it is cosine minus cosine.
Oh. Yes, you are absolutely right. One minute. Yes, here this is this part is a rho, this part is a phi, and according to the formula, there should be another row with this one, another row with this. And when we have another row with this, any row, and then a phi, component of phi, rho square derivative of with respect to rho is 2 rho cosine phi, minus derivative of 2 rho sine phi with respect to phi is also 2 rho cosine phi. So this is equal to 0 vector. Thank you. I just overlook this and move quickly. There exists a potential function V such that this electric field E is equal to negative of gradient of V, del V. Okay. Now, we are not in Cartesian where things are very simple. Here we are in what field? Coordinates cylindrical. In cylindrical, the gradient V is defined as, you can have the formula sheet. You have formula sheet from the previous chapter. It is negative, and what is the gradient? Partial over partial rho, then 1 over rho partial V by partial phi. So we have 1 over rho here. And then the third component is partial V by partial Z. So this implies partial V by partial rho is equal to negative of the first component of E 2 rho sine phi. So it is a negative 2 rho sine phi, and partial V by partial phi, rho will be multiplied over there, so it will become rho multiply rho cosine phi, and partial v by partial z is equal to 3z square. Of course, now we have a negative with them also. Integrate any one of them. Let us start with the first one. The first one implies, this one implies v of rho phi z. So for simplicity, v is equal to negative rho square sine phi plus a function of phi and z, some function of phi and z. After this, we differentiate this v with respect to phi. So negative rho square cosine phi plus partial f over partial phi, and we put this equal to negative rho square cosine phi. Now this implies rho square cosine phi cancel. That partial phi f by partial phi is constant. With respect to phi, constant with respect to phi, yani there is no phi there. So it means it is a function of z alone, no phi. Function of z alone. So, equal to 0 implies f of phi z is actually a function of z alone. There is no phi there because derivative with respect to phi is 0. So with this, we get g equal to negative rho square sine phi plus g of z. Now we take derivative of this with respect to z. So it is 0 plus g prime of z, and we put this equal to partial v by partial z, which is negative 3z square. And when we integrate, we get g of z equal to negative z cube. So at the end, we get v f rho phi z equal to negative rho square sine phi minus z cube. So this is the potential function phi, whose gradient is negative e. Now we're done with part B, and part C is the use fundamental theorem and evaluate this integral. So part C. Potential function V at the point 2, V at A is 2 pi over 6 negative 3. Let me see, 2 pi over 6 negative 3. And this will give us negative, rho is 2, so it is 4. Sine pi over 6 is 1 over 2. And negative minus of negative 3 power 3. So it is a negative 2 plus 27. So it is 25. V at this point, then potential function at the second point, end point, which is 4 pi over 2 and 2. This is 4, so negative 16 sine pi over 2 is 1, and then minus z cube minus 8. So this is equal to negative 16. So this dot is not point, this is multiply. 16 and 8 is 24. Okay. So this integral, they are saying evaluate this integral. 2 pi over 6 negative 3 up to 4 pi over 2 comma 2 e dot dl. This is equal to v at 4 pi over 2 to v at b minus v at the end point from A to B. So what do we get? Negative 49. Any question? Yes.
In the last equation, how did you get the integration of E multiplied by dl is equal to v minus v2 minus v1?
This is what we did yesterday, that if E is conservative, E can be written as a negative of gradient of V. So since we know that E is conservative, so E can be written as negative gradient of V dot dl. And point is same, 2 pi over 6 negative 3 and 4 pi over 2 and 2. So, and then the fundamental theorem says that this is equal to V at the end point, which is 4 pi over 2 and 2 minus V at the starting point, 2 pi over 6 and negative 3. So actually it is 49. Okay, here. In 9.9, we have this fundamental theorem. Actually here, when in our course we are using notation E, so we have this negative sign. So we will have negative V of B plus V of A. So it is from the fundamental theorem. Before you are using this as a fundamental theorem of calculus. But here is, we are just simply saying fundamental theorem. So by that theorem is negative gradient of V. So it means negative into V of B minus V of A, which actually become V of A minus V of B. So it is 49. And what left is calculate the work done in moving charge 5 microcoulomb from A, this another point A to another point B, not this point, another point. So part D is that V is equal to negative rho square sine of phi minus z cube, and this time V at point A, yani V at 1, 0, -2, rho is 1, phi is 0, z is -2. So phi sine 0 is 0 minus -2 cube is -8, so it is +8. And V at B is equal to V at the second point, which was 4, pi over 2 and 1. Point B, 4 pi over 2, 1. 4 pi over 2, 1. So here, pi over 2 sine pi over 2 is 1, so 4 square 16, so minus 16. Z is 1, so minus 1. So this is equal to minus 17. So the work done is equal to negative Q time from A to B E dot dl. Negative Q, and then E dot dl will give us V at A minus V at B. Actually, so we will put these numbers here, minus 5, and inside VA minus VB will be equal to A8 minus negative 17, so plus 17. 18 plus 17 is equal to 25. So this is equal to negative 125 microjoules. So this is work done. And here about the work, it is negative or positive. It is explained here in this note. And you are electrical engineer, so you know much better than me about these terminologies. Okay, so this is about the same thing. We did one example yesterday, and that example was using Cartesian coordinates. This example is using cylindrical coordinates. You may have some problem to do in spherical coordinates. Okay, so you need to remember these things. Like the only thing is we have electric field, we find potential function, use fundamental theorem, and evaluate. That's it. Nothing more, nothing less. Okay. So this is what we have this from this 4.7, which is what is the name of this one? Electrical potential.
Doctor, is it with us in the midterm?
Okay, one thing, Shabab, it's good that you ask me that what I wrote you in the Blackboard announcement that 9.9 was included, but no. This 9.9, 4.7, 4.8, these are something which is not included in this this first major. From chapter 4, actually 4.7 and 4.8, I'm saying 4748, that is from chapter 4. So 4748, 48 we have not done yet, but we will do 48. And 47, what is this 47 electrical potential? And we are doing these problems about electrical potential right now, and also work done by electric field. So this thing, independent of path, this is not included. This is not included in this major 1. This will be included in the final. Okay? Yes, Shabab?
Doctor, that means chapter 3 and chapter 2 and the...
Chapter 2 and 3 are included.
Okay.
But 9.9 and chapter 4 is not included. Because that becomes too much.
Yes, thank you, Doctor.
You want to include? I can include. Still there is a time.
No.
No.
I think you want to include.
No.
Okay.
No, thank you, Doctor.
All right. Okay, so...
Doctor?
Yes, please.
So they made only until chapter 3?
Chapter 3 only.
Okay.
Okay, because that become too much even. So from 4.7, we have a electric field and electric potential, a point charge from A to B on electric field. When we move this charge, we do some work, and that is equal to negative, and Q dot, then the total work is from A to B, this integral, and the potential difference is the mean loss in potential energy, that is VB minus VA. And potential at any point here, okay, potential difference, and you can say potential at any point. So we say is equal to V is equal to this Q over 4 pi epsilon naught and R, where epsilon naught is equal to D over E. So actually these are vectors, so we should write here where D vector is equal to epsilon naught and potential E, and this D is electric flux density. And E is something we have already written here. It is the electric field. And so we have this thing, relation between, now this is something from next chapter, actually next section, which is section 4.8. That's enough from previous section. So this is uh, 4.8, and this section 4.8 is, there are some more questions here. I'm seeing more questions in your book in section 4.7. Try to solve. I show you one in Cartesian, one in cylindrical. You can have more practice by solving some more examples and practice questions and practice exercises in the book. Relationship between E and V. Although we have done this, I think it has a name, Maxwell's equation. Okay. Potential difference between 2 points A, B is independent of path. So that is why we were using this idea in before that E dot dl can be written as gradient of A, and E can be written as a gradient of V. Independent of path, yani V from A to B is same as V from B to A, VAB and VBA are equal, but of course in direction is opposite, and you also know this from definite integral. Integral from A to B is equal to minus integral from B to A. So that is why V from A to B plus V from B to A, which is over closed path. You go from A to B, then come back from B to A. Over closed path, I'm making here a small circle over L, whatever L you choose, E dot dl. I think we wrote this a theorem in the previous section that if path is closed, then this integral is equal to 0. This integral is 0. Okay, along a closed path. A circle is telling us closed path. What does this mean? That no net work is done in moving a charge along a closed path in an electric field. No net work is done in moving a charge along a closed path in an electric field. Actually, this is more than simple electric field. It is electrostatic field. And what is Stokes theorem? We learned before. We learned before Stokes theorem that integral over a closed path E dot dl is equal to integral over surface del cross E dot ds. Del cross E dot ds. Stokes theorem. So if del cross, if E dot dl, this integral is 0, then the other integral is also 0, and that implies del cross E, this is equal to 0 vector. And a curl is 0 mean. This mean that the electric field is conservative what is some other, say, name which we can use for conservative when del cross E is 0? Irrotational. There is no curl. There is no tendency of rotation. There is no tendency of rotation. Okay. Now, let us do some questions to make these things more clear. Example. What is this example? A point charge of something 8 microcoulomb is located as at point 1, 0, 0. So it means it is located on x-axis. While the line y equal to 2 y equal to 2 and z equal to 3. When these are these two are together, we say a line y equal to 2 and z equal to 3. We say this is a line. Okay, let me remind you, I will erase this. In Math 201, section 12.5, you know, parametric equations of a line. X is equal to x naught plus at, y is equal to, come on, you should not do this. This one note is hanged. Let me restart this. Sometime it happens. Okay, and share with you again. One note here is. Okay, so we are back. Parametric equations of a line. If you remember, we write x equal to x naught plus at, y equal to y naught plus bt, z equal to z naught plus ct. Now, then how this y equal to 2 and z equal to 3 are here? We have x equal to 0 plus 0t, y equal to 2 plus 0t, z equal to 3 plus 0t. So these are parametric equations. We can also look this line as line of intersection of two planes. One plane is y equal to 2, which is a plane parallel to xz plane. XZ plane, a plane between z axis and x axis. This line y equal to 2 is a plane parallel to xz plane, and z equal to 3 is a plane parallel to xy plane. One plane is horizontal and another plane is vertical. One plane is horizontal, another plane is vertical. And when these two planes intersect, they will give us a line parallel to x-axis. So let me put in the bracket a line parallel to x-axis. We have this type of thing once before. So while a line y equal to 2, the line y equal to 2 and z equal to 3 carries a uniform charge. How much? 3 microcoulomb. So we have a point charge and a line charge. If the potential at point A which is 0, 5, 3, so we are in Cartesian coordinates, is 30 volts. What is the potential at the origin, which is 0, 0, 0? So the situation is this one. Let me try to no. This doesn't look good. Let me make by my hand. This is much better. We use this as x-axis. This is y-axis, and here is going above z-axis. And we have a point charge here, which point is 1, 0, 0. X is 1, y is 0, z is 0. And y equal to 2 and z equal to 3. This is a line. When y is 2, z is 3. We have, let us say, this z equal to 3. This is the point when y is 2, z is 3. Okay. And this point, this is the line. And a line, this line is a line which is parallel to x-axis. This line is parallel to x-axis. So let me try to make a line parallel to x-axis. A line y equal to 2, z equal to 3. Then we have a point A, 0, x is 0. So it means this point is in YZ plane. X is equal to 5. Y equal to 5 and z equal to 3. So here, let me use a small, there's a small units. 1, 2, 3, 4, 5. And here, let me make a line parallel to x-axis. 1, 2, 3, 4, 5, and y equal to 3. So z is equal to 3. So let us say this point is A, 0, 5, 3. And that is a line parallel to x-axis. Okay. And we need to find what is the potential at the origin. I will continue from here because it is now time to leave. And tomorrow, yani on Sunday. But Shabab, on Sunday, first I will answer your questions. If you have any question about the material which is included in the exam on Sunday night, you know that on Sunday at night 7 p.m. you have your first major, first and only major. You know the location, Shabab? Can someone tell me what is the location?
Building 11.
Room?
131.
131.
Exactly. Room 131, building 11. So try to be there at least 30 minutes in advance so that we can start the exam in time.
Doctor?
Yes.
Yes, doctor. If you can that suitable with you, you can make a help session in Saturday.
On Saturday. I can make help session on Saturday. Help session mean question answer session. You ask me question, I will answer. So on Saturday, at what time you want?
Anytime, but I meant we solve questions about chapter 3 from the book or old exam or whatever.
Yeah, chapter 3, chapter 2, you solve the questions about everything in this included in this exam. So then on Saturday, what time? You tell me the time.
Anytime suitable with you, Doctor. I'm free all this.
10
day.
o'clock is okay?
With me is okay. With,
Yeah,
my
Shabab, any other? Okay. So those who are listening, this is for them. Shabab, on such a day, I will be online at 10 o'clock. And if you have any question, you can ask me. And I will be online in this meeting room, yani in this class. So you don't need to call me separately.
Do you mean 10 in the morning, or at night?
10 in the morning, of course.
Can you make it like maybe 6 or 7 at night?
You know, on weekend at night, someone may have some family commitment. I may have some family commitment, so that will be difficult.
Can you record it if you can?
Of course, I will record it. If someone remind me about recording, I will